section 2.4, we're going to encounter something called a product rule and a quotient rule. And these are the very first times where what we want to be true isn't going to work out for us. So let me show you what I mean. So the first one we're going to take a look at is the product rule. And what we would kind of like to be true is we would like to be able to take two functions that are multiplied and then find the derivative. And we kind of like to be able to find each of the individual derivatives and then multiply the result. That's what we would like to be able to do. It seems intuitive. It seems natural. It sort of matches the sum and difference ones that we had, right? Just take the individual pieces and then multiply the result. Please note that it says question and there's a question mark at the end of that. Okay? We're going to see if this works, and we're going to use pretty simple functions to do it. This f of x that I'm defining is 4x to the 9th, and then the g of x is x cubed. What we're going to do is we're going to try to do both sides of this equation that's got this question mark on it above and see if it works out to actually being true. Okay? So if I do this on the first half, it means I should take the two functions inside and multiply them. So I should take 4x to the 9th times x cubed. So how would that simplify? What is 4x to the 9th times x cubed? 4x to the 12th. All right. So this would be 4x to the 12th. And then let's use the power rule. What is the derivative of 4x to the 12th? 48x to the 11th. Is everybody good with that? Okay, so this is the correct answer, obviously, to the question because we did all the algebra inside and we actually took a derivative at the end. Our question is whether or not we could have taken the individual pieces derivatives and got the same answer. So on this problem, we wouldn't have tried to do that because it was simple enough to do the way it was already done. But you're going to see cases where it would be much better or simpler, easier, more convenient, or flat out the only possibility to do the individual derivatives in some form instead of combining them first. So let's take a look at this one now. This says that I could actually, or question is, could I take the individual derivatives? Well, f of x is 4x to the 9th. So what is the derivative of 4x to the 9th? That would be 36x to the 8th. The other piece, g of x, is x cubed. What's the derivative of x cubed? 3x squared. So what is 36x to the 8th times 3x squared? It is 108x to the 10th. And you notice, lo and behold, what? These are not the same. It doesn't work. Man, I wish it did, because it would make things a lot easier. The answer up here is no. Please, 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 write this down. This does not work. Okay, so what in the world is the product rule actually going to work out to be? Well, this is actually how it works. If you want the derivative of f of x times g of x, what you have to do is you have to take the individual derivatives. See that g prime and that f prime? They're in there. But you combine them with each of the functions as they originally were. So there's variations of this because commutativity of both multiplication and addition. But the basic idea is that you leave one portion the same, and the other half is you take the derivative of each of the others. So let me just do the one that I did before to show you that the example I gave before, it really did work, because I actually showed you it didn't work with the other sort of supposed thing we'd like to have had happen. So if my f of x is that 4x to the 9th, and my g of x was x cubed, right? Did I get those right? Okay, good. Then if I were to do f prime, we already did this, we got 36x to the 8th, and g prime, you had 3x squared, right? So what this problem is actually saying is, or what this rule is actually saying is that I take f of x, which is originally given 4x to the 9th, I multiply that by the derivative of g, which is 3x squared. I add to that the derivative of f, which is the 36 x to the 8th, and I multiply that by the original of the g of x function, which was x cubed. Right? This is a more complicated process than what I would like to be true, but we already showed the one that we would have liked to be true didn't work. So what is 4 times 3? 12. And then I've got x to the 9th and x squared, which gives me x to the 11th. Over here I actually have that 36, right? X to the 8th and x cubed is x to the 11th. And then I have 12 plus 36 is 48, x to the 11th, which is exactly what we were trying to get the other one to equal. I will. So doing these in these little pieces in this process, it actually worked for this function. Okay, and it works for all functions. This really is the product rule. Okay. What I was mentioning before the screen went out just a minute ago is that there's variations on how to write this. I like to do it in this order because it means that the first piece of information I write down, I don't have to do anything. I already have it. I know I can start the problem because the problem starts out with a piece I already know. I know f of x. It was given to me. And then I've got the derivative part after that to do g prime of x. So that's why I do it in this order. I'm not sure what order your book does it in, but it doesn't make any difference. You'll get the same answer when you simplify. Okay, we're going to try a couple. Are you ready? All right. So this first one, obviously, we could actually multiply this out, right? And we could do the rule. We could actually have done this problem in the last section without the product rule. But I want to show you how the product rule works by using this example, and we'll give it a go. So we're looking at the derivative. To do the derivative, the first thing I do is I just simply rewrite the first piece. Okay, so you can always start. The second thing I do is I take the second part of the function, x squared minus 5, and I take the derivative of that piece, which is 2x. Then there's an addition sign. That's part of the rule. And then I will take the first function, x squared plus 3, and I will take its derivative. And what's the derivative of x squared plus 3? 2x. And I will multiply that by the original second function that I was given. And at this point, you've done all the calculus there is to do in the problem. Everything else is algebra. It's all algebra. And it's not terrible algebra either. This is actually pretty clean. So I'm going to distribute the 2x, and I'm going to get 2x cubed plus 6x. You got it? And then I'm going to distribute the second 2x, which is just happens to be what it works out to being, and I've got the 2x cubed again, and minus 10x. And if we combine like terms, what does that give us? 4x cubed minus 4x. Yes?
How is the derivative just 2x? Unlike just...
It's the derivative of each individual pieces.
How does it not have like the 3?
Because what's the derivative of 3? 0. The derivative of the 3 or the 5 is just 0. That's the constant rule from the last section that we were doing. So you're right to ask, though, Grace, why in the world did I start with something that has 2 terms and it all of a sudden becomes 1 term? That can only happen if I've got a constant feature, which these actually both happen to have that. Our next problem is not going to have that going on for us. So you're going to see more terms in the next problem because I don't have all constants like this one had quite a, I mean, half of the terms here is constants. So. Do you guys have another one in your homework? Okay, I thought so. I don't know why it's missing from my notes, but without a doubt it is. Okay, let me write it in over here. Okay, did I get it written down correctly? Does it match? Okay. And this is problem number 2. All right, so we're going to take the derivative of this one, and we're going to do that by the product rule. So the first piece I'm going to do is I'm going to just rewrite what I've already got. Now the second piece does happen to have a constant in it, so that derivative of the negative 2 is 0. What's the derivative of the x to the fourth? 4x cubed, right? Yep. All right, so this one now I'm going to do the derivative of the x to the 3/2 minus 4x. There's no constants in that one, so I'm going to get two terms because there's two terms in the original function. What's the derivative of x to the 3/2? Right, 3/2 x to the 1/2. Is everybody good with that? Okay. And then what's the derivative of the minus 4x? Minus 4. And then I'll multiply that by the original second function, which was x to the fourth minus 2. And again, at this point, we're done with the algebra. With the calculus. Everything that's left is algebra. Okay, so is everybody good with this to this point? Do you have any questions on any of the pieces?
So how come the x to the 3/2 minus 4 isn't like minus 4x?
Because the derivative of 4x is the same as asking the question, what's the slope of 4x? And the slope's 4.
Just f of x?
This piece right here, oh, you're talking about there.
Yeah.
I'm sorry. Yeah, it's left out right there. It just was a mistake, but we'll fix it. Thank you. I thought you were talking about the other piece over here. Okay, so are we good now? Any other pieces that are not done properly are okay? Okay, great. So we're going to do some distributing, right? We're going to actually simplify what's here, see if we can combine any terms. So the original problem, or the original first piece here, the x cubed, x to the 3/2 minus 4x times the 4x cubed. I've got to multiply these two pieces together. So there's 4x to what power? Yes, it is 9/2. All right, we're doing 3 plus 3/2, which is actually 9/2. And then I have minus, and I have 4x times 4x cubed, which is 16x to the fourth. The other piece is actually a little bit more challenging because I've got two terms times two terms. So we'll do the outside terms here. So I have 3x squared, 3x to the 1/2 times the negative 2, which gives me a negative what? Negative 3x still to the 1/2, right? These are the outer terms. I don't know why I did that one first. Just for fun, we'll just do it all out of order this time. We'll do the inner terms. What's negative 4 times x to the fourth? Minus 4x to the fourth. Let's do the first terms right here. So I've got 3/2 x to the 1/2 times x to the fourth. What's that one going to give me? Well, we had x to the 1/2 and we've got x to the fourth. So what are we going to do to combine those? We add them. So what's 1/2 plus 4? Yeah, it's 4.5, which is 9/2. And then the last term, since I still ended with L, into 9 and FOIL, last terms. I have negative 4 times negative 2, which is? Plus 8. Okay, is it all there okay? Some of them combine, don't they? A couple pieces do. What do you see that combines? Somebody give me an example. The 9/2 and this 9/2. So I have 4 and 3/2. So how much is that? That is 11/2 x to the 9/2. Okay, so I've taken care of the 9/2 parts. What else can combine?
The 4 x to the 4s.
This one and this one. So how much will those combine to? Negative 20 x to the fourth. And I think the other pieces stand alone, don't they? Minus 3x to the 1/2 plus 8. And actually, that is in decreasing order of exponents because 9/2 is actually 4.5. So it's actually the largest exponent. It doesn't actually have to be in that order. We've talked about that before, but in this case, it actually was. Any questions on this one? Okay. Let's take a look then at the quotient rule. All right, so this screen looks a lot like when I was showing you the product rule. The question being that if I want to take the derivative of a quotient, could I just take the derivative of the top and the derivative of the bottom and combine them with division? And so we're going to use the exact same f of x and g of x functions that we had before. And as you would guess, we're going to show that it doesn't work, right? So let's take a look at these. I should be able to take the 4x to the 9th over the x cubed. I'll reduce them, and then I'll take the derivative. So what would those reduce to? I'll start. 4 what? 4x to the 6th. Okay, and what is the derivative of 4x to the 6th? 24x to the 5th. And that is the correct derivative of this function. That is absolutely 100% correct, because all I did was simplify the algebra first, and then I did the derivative that I know worked. Okay? Our question is, could I have done it in the reverse order and it still have gotten me the same answer? So I should be able to take a look at that by doing the derivative on the top and the derivative on the bottom, and then doing the algebra. So what is the derivative of 4x to the 9th? 36x to the 8th. Someone else, what is the derivative of x cubed? 3x squared, that's right, Shannon. And then we can combine them, right? In this case with division. So how will this simplify? 12x to the 6th. Nathan, did it work? Are they the same? No. These two are not the same. So does this work? The answer is no, it does not work. Absolutely no chance. So there's something wrong with how we've set that up. And it is not quite even as clean as the last one on how we do this setup. So let me show you once you're done writing. Where's the actual one? Fantastic. It's not on here. I'm really struggling today with these slides. I don't know why. All right. I'll write it out. All right. So what is the quotient rule? Well, the way that the quotient rule works is that you take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Does that look sort of like the product rule? It's very similar, except it's got a sign of subtraction in between it, right? But all of this is written over the denominator squared. So would you like to see the mnemonic that I was taught when I was in high school about how to remember which piece goes where? You can memorize it just as is, and that's fine, but there is actually a really nice, a couple of them I've seen before. I'll just show you one of them, is to think of this as written as hi, ho, you know, like the Seven Dwarfs, hi ho, it's off to work we go, okay? So this is ho-de hi minus hi-de ho all over ho-ho, like Santa Claus. Hi-de ho! Does anybody know what that's from? I think it was from Tool Time. Is that right? So before you guys' time, I just dated myself, didn't I? All right, so this is one of the ways. I've also seen this written as high over low and done the same thing, okay? So I will promise you that whenever I do a quotient rule, this is what goes on in my head, because this is the mnemonic that I was taught. So I always think, oh, that's how I start. I start with the denominator because it's ho-de hi. All right, so before we head on out, let me take a look with you on getting one of them set up. This one right here, number 3. So this this quotient rule, says that what I have to do is I take the denominator, which is 5t minus 3. I multiply that by the derivative of the numerator. So what is the derivative of t squared plus 4? 2t. Because it's a quotient rule, it's subtraction. So then I subtract the numerator, t squared plus 4, and I use the derivative of the denominator. What's the derivative of 5t minus 3? 5. And all of this is written over the denominator, quantity squared. That is all the calculus there is, folks. Everything else is simplification of algebra. So the numerator becomes 10t squared minus 6t minus 5t squared minus 20 all over 5t minus 3 quantity squared. If I combine things in the numerator, what do I have?
5t squared minus 16 minus 20.
All over the same denominator I had before, right? It's a good idea to look to see if anything in the numerator can simplify. I know there's no chance of that happening, although I have a 5t that this could factor into, like a 5t and a t if I were to split it up. 20 doesn't have a factor of 3, so I can't get a factor of 3. So the only way this would simplify is if there were a 5t minus 3 factor on top, and there isn't. It's not possible. It's very uncommon once you get to the quotient rule at this point that things factor out cleanly. Occasionally they do, but it isn't the norm. So this is our derivative then. This should have said prime. Make sure yours says prime. Mine was left off for some reason. This is the derivative of g.